Hello GGS300, thanks for tuning in again today to what is the second lecture for this semester for GGS300 Quantitative Methods for Spatial Science. Today we're going to be focusing on the introduction to geographic data. Okay, so just a little bit of a course update before we begin. I will be setting the first assignment this week. It's not too arduous, so it's a lot of the material that we essentially covered within that first lab session. So what's really key here is that you've managed to either install the R software on your own machine, or you've managed to get access to the R software via the GGS virtual laboratory, okay? So I've had quite a lot of emails from you in order to try and get it installed on your own machine, so I hope that by now we've managed to overcome a lot of those issues and get you going basically on your own version. So reach out to me if you've got any further problems, but hopefully after this week we've ironed out that process and you'll be able to just focus purely on getting the work done, which obviously will be assessed. Okay, so that'll be in the assignment tab within MyMason for this course, and you'll need to also submit that assignment via that assignment tab once you've completed it. So the key point to remember is that you need to put all of the graphs that you generate into your submission, and you need to paste the code in as well at the end of your submission. And remember that your code needs to be neatly written, preferably annotated, so that it's easily understood by another person, because at some point you might be sharing your code if you go on and you do further research, or you work in a place, an employer in a company where you're actually doing this analysis. You need other people to be able to understand what you've done, so that's important. Okay, great. So that's the assignment. Hopefully everything is in order there. So just reach out to me if you're stuck on any further issues. Fantastic. So in the presentation today, I'm going to be introducing you to different aspects of data. There's going to be a particular kind of spatial angle to that, given the relevance of this course. It may have overlapped. Some of this content may overlap with work that you've covered already in other courses. That's fine. If you're already familiar with it, then this is a good kind of session to reinforce that knowledge and understanding. If you're new to this, then you need to basically learn the definitions and really kind of get a feel for those different aspects of the data that we're going to be discussing. So there's different dimensions to data, and you just kind of need to know them because you need to be able to think critically about the different data sources that you either might use or have used in a model that you've built or a piece of analysis that you've done, in order to work out if you've actually measured what you intended to set out to measure. Okay. So we all think about statistics on a daily basis, whether we know it or not. Okay, so I'm going to give you some examples of where we're actually always engaging with quantitative information. And one place is obviously technology. So we're always locked on our smartphones. However many hours a day, probably about 2 hours a day, I'm using my smartphone, constantly looking at different dashboards of data that's being collected. So this is just an example for my Fitbit data. It's just basically providing a dashboard for the number of steps that I've taken, my heart rate, the number of floors that I've climbed, and these are just basic statistics, okay? So it's been collecting data all day long, and it's providing a single metric to represent all of those different data points over some sort of arbitrary time unit, which for a Fitbit is generally every day. Okay. So that's the left-hand side, where we've got some basic descriptive statistics, which we will be covering in greater detail next week. And then the right-hand side, we've actually got temporal data, okay? So this is data that has been collected along a specific time dimension. So this is actually my heart rate collected over a specific day. So I probably should have been doing some more exercise, but I think it's okay. About 60 beats per minute resting is actually pretty good. So that kind of gives you a flavor for the type of temporal data that we may all engage with on a daily basis. And if you're using Strava or one of these other apps, then you'll be very familiar with looking at this type of temporal data. If you're into markets, then obviously you're used to looking at changes in price signals over time. So this just to give you an example here for the S&P 500 index. So this is the top 500 largest companies in the United States. And at the bottom here, I'm just giving you an indication of the overall price of the index. Essentially, you can see a big dip in the middle there, which was March, April May last year when COVID first started taking off. And actually since then, it's really picked up quite a lot, mainly because it's so tech heavy and tech's really done so well in the last year. So if you're interested in markets, if you're interested in currencies, then you'll be used to looking at time series data for different metrics of interest. Okay, so you'll be good at grasping how to understand this type of visualization. And then another source of data that probably many of you have encountered already if you're working on GIS is actually data from the Census Bureau. So if you're working in geography, that might be quite common. Actually, a lot of my funding was from the Engineering Research Council for my previous work, and I was using census data all the way through that. So if you're trying to look at the number of people who may be flooded under different scenarios, then you need some understanding of where people live and who those people are, and the way to do that is to get spatially disaggregated, high-resolution demographic data, which obviously is predominantly from the census. So you need to go and get at least some base data from the Census Bureau, even if you then decide to do your own forecasts for those demographic trends. So do check out the census website if you haven't already. I'm sure many of you will be used to looking at data from here, but there's a lot of good socioeconomic data on here. I haven't mentioned also the economic bureau type of data, but labour market data, employment data, that's also very good stuff to use if you're interested in trying to get an understanding of firms, employment, where economic activity takes place, all within a pretty good level of geographic insight. So I think here you can go down to census tracts, which are obviously very granular in the US. So yeah, you might be used to engaging with data through the Weather Channel or through the news. So actually I had a conference that was always in the US in September, so I was always there during hurricane season, and it kind of struck me how much we were kind of engaging with those kind of modeling forecasts on a daily basis. Okay, so there's a hurricane blowing in, you don't know where it's going to make landfall. Essentially, the NOAA or other organizations are trying to make predictions as to where that's going to happen. The way that they actually do that is they may run a model that they have thousands or millions of times on a very powerful computer, and then what they do is they average the potential forecasted route across all those different predictions. It's called ensemble modeling, and they might produce an average route that they think is most likely, and they'll provide some confidence bounds either side, and that's how they actually do these potential forecasts, which obviously we all rely on a pretty much daily basis to get a weather forecast. So this is kind of nice information, and there's actually statistical techniques within how they develop these forecasts that we will be touching on within the next few weeks. So how do you make an estimate for something and then provide a confidence interval? So how confident are you that the number that you have provided falls within a specific range, for example? So you might be engaging with data through the Weather Channel on a daily basis. So there's some of the sources of data that you might actually be accessing. Now let's consider more of the kind of scientific spatial issues associated with this type of data. And as I mentioned before in the previous lecture, when I was talking about Bacon and Newton, we're going to be focusing on mainly scientific analysis here, and science is obviously quantitative, so quantitative information is essential to that whole process. But it raises a whole load of questions such as, well, what is science? How do we do science? How do we collect data? What do we actually do with the data once we've got it? Okay. So just to give you an example, this is kind of the classic research project that might land on my desk. So there might be a question, how do we provide universal broadband to everyone across the African continent by, say, 2030 in order to support the Sustainable Development Goals? So this is a project which I've been working on for the World Bank, which is pretty fun. It's got some pretty cool geographic data in it. I actually have a model that makes estimates of the cost of providing universal broadband, essentially, via different technologies, and that is able to kind of build off insights on the population density, which I'm able to extract from the global satellite layer, global satellite information. So on the left-hand side here, you can see that there's a map of the population density. So it's very, very dense on the North African coast. in the Mediterranean. Then you've got the Sahara, where you've got very low population density. Then you've got that band on the West African coast, where you've got very, very high population density, as well as in the eastern part of Africa as well. So that just gives you a kind of flavour for where the people are that you might need to connect. And then on the right-hand side here, you can see that I've actually produced costs for the potential cost of delivering broadband to those people based on the existing level of infrastructure and how much additional infrastructure you may need to build. Okay, so this is kind of giving you a flavour for the type of data that we might need to use as an input to our model, such as population density. In order to answer a research question, how do we provide universal broadband? And then it's providing us with some metrics as the model outputs, essentially. So the right-hand part of this slide, which provides us insights on essentially how much it may cost to actually meet that research question. So this is a fairly standard type of project, which then I'm able to write a research paper on it, or actually use the analytics to help inform how the capital is spent at the World Bank. So the World Bank spending over $1 billion worth of funding on digital development projects over a 5-year period on broadband or ICT skills. So this type of work helps to inform how you spend that very large amount of money. And I think the important thing is that if you even just make a 1% efficiency improvement on an amount of capital that size, it has a really dramatic effect. And that's really what's exciting about the type of analytics that we're producing here, and the type of analytics that you can learn how to develop through this course. Okay, so that's an example. What's the actual process? Well, we may start with a research question, okay? And how that question is actually obtained may depend on a variety of different things. So I've just put at the bottom here that, a standard way is that an academic might look at the theory across an area on a particular subject that they're interested in. Then the academic or the person in industry may develop a research question, and then they may go out and collect empirical data, so actual data from reality. So theory is an expectation for how we think the world works, but yet we haven't proved that it's truth. Empirics, as we discussed last time, focusing on Francis Bacon, is a way to collect data through observation to try and understand how the world works. So we can pose a question, we can collect some data, and then once we've drawn conclusions from that, we're actually able to then circle back to theory and reinform how we think the world works, okay? So this is potentially a way that an academic may develop a research question for inquiry. You then need to go out and basically develop a method to answer that research question, and then you need to discuss the ramifications of it and link it back to theory. So this is kind of, in very general terms, how we do science, okay? And if any of you are going to go out and try and write a research paper, maybe you're going to do a dissertation, then this is the kind of process that you need to be aware of. And it's exciting, it's hugely exciting. This is the way that you work out new things about how the world works. So in trying to answer that research question that we posed, we need a method. And to do that, we need data, or at least some understanding of the data that's available to us, even if we haven't collected it yet. So we need to understand what the different aspects of data may be. So that could be qualitative, it could be quantitative. Within quantitative data, it could be discrete data, it could be continuous data, it could be spatial data, it could be non-spatial data. There's a whole raft of different aspects to that data that we may need to collect. And then that data is going to have specific characteristics that make it relevant for certain methods, so modeling methods that we may want to use. Okay, so we need to think about that when we're actually developing the method for how we answer that research question. And then within this course, we'll also be covering later sampling methods. So there's a question, well, how do we actually collect the data that we need? It's nice to have data already collected. I love having data that's already had the hard work put into it, but often we might need to go out and collect our own data, okay? In which case, then we need to know how we actually design a scientific experiment to collect that data. We need to make sure that we control for a range of factors that can affect our data metrics. Okay, so this is something that's really critical and something that we will be getting to within about week 4, 5, 6, we start to get into sampling. So I didn't get into this last week, but for those of you who read the chapter in the book that you were supposed to read, you'll have noticed that there was some kind of diagram that was essentially there to provide information on how you actually carry out a spatial scientific process. And this is my kind of take on that. And essentially, it kind of fits into the way that the module is structured, okay? So this left-hand part where we identify a problem, could be from theory or it could be a problem that we're facing in real life. We then develop questions to investigate that problem, we collect and prepare data, we process the data, and then we reach conclusions. That whole process there is basically focusing on descriptive statistics. Okay, so that's what we're going to be doing in the first third of the class. So that's the next 4 or 5 weeks. And then what we have towards the kind of right-hand side here, my right-hand side, and the bottom part of this diagram, is actually moving towards what is called inferential statistics. Okay, so maybe you were able to formulate a hypothesis for how we think the world works, and then we want to go out and collect data to work out whether that hypothesis can be accepted or whether we need to reject it. Okay. So we need to be able to test that. So we need a formal statistical test, and then we need to evaluate the results that we get for that. And that's how we get down to the bottom of this part here. So this is essentially the latter 2/3 of the course focuses on these inferential techniques. And then once we've actually made a decision as to whether to accept that hypothesis or reject it, we actually then go back to refine the theory or the model from the beginning, or we go on to make the world a better place. So we gain impact from those decisions. So we gain impact by influencing decisions that people are making in the real world. So that's me basically producing results which can inform how the World Bank decides to spend very large amounts of money. Okay, so I think that provides you with a general overview for how we go through the spatial scientific process as I kind of see it here. Within this class, we're here to focus on different aspects of data, and part of that is actually kind of thinking through a range of different aspects of different different issues that your data may encounter. Okay. And these are somewhat different from those typical kind of issues that you might encounter in a standard statistical class. Okay, so there are issues that will arise with non-spatial data, so aspatial data. But here, because it's a spatial science class, I'm going to be particularly focusing on those aspects which will affect our spatial data. And you know, these aren't always picked up by other people who work outside of kind of spatial science, and therefore it can have a serious impact on the results that you produce, and therefore the conclusions that you draw. So it's quite an important area to be aware of. So out of those 4 different areas, we're going to start now focusing on boundary delineation. And it's very sad, I know, but you know, this is one of the things, particularly when I show you the paper I've been working on recently, that does worry me. It does keep me up at night, along with unit errors, which are another potential source of error within your academic work. So yes, it is concerning, and you do need to be aware of these different aspects. So what is boundary delineation? Well, I think the important part here is that, remember, we create artificial spatial boundaries, and then we actually aggregate data within it, and that's all artificially imposed. So just bear with me, I'll provide you with descriptions of exactly what I mean, using examples that are common to your understanding. So for example, I spoke previously about the role of the Census Bureau, and the Census Bureau there is there to, you know, for one function, every 10 years, go out and carry out a census of the population. So it's going to be collecting information on socioeconomic characteristics, age, gender, all sorts of different aspects that are relevant to society for which we need data on, okay? The key issue, however, is that many of those boundaries which we collect the data within and then aggregate it in afterwards are actually artificial. Okay, so this just gives you an example here of Fairfax City, which you can see in the very center of the slide, and then Fairfax County, which you can broadly see around the outside, which encompasses quite a large area of North Virginia in this particular shot. That's all artificial. We create those boundaries, we change those boundaries. Sure, in some extent, to some extent, it does follow the natural watercourse here, but we still decide that we want this boundary to follow that particular watercourse. So there are issues then in how we draw these boundaries because it actually affects the results that we generate, and that's really the crux of the argument. Okay, so that was quite aggregate before. When we look here, we've got quite large areas, multiple tens of kilometers for even one of these smaller blocks, smaller areas within Fairfax County. What happens if we use a much more granular level of insight on population? So what happens if we use a 1 kilometer squared level of data insights, so for the census boundaries? Actually, for the project which I showed you before, where I was working on universal broadband for Africa, I use a 1 kilometer squared data set for population so that I can get population density at a really small level. And the reason why I do this is that then when I aggregate the data, which I'm going to have to do at some point to some sort of political boundary or artificial statistical area like a region or a country, I have full control over the data that I pull and aggregate to that level. And it's for this exact reason that it changes the results that you get depending on how you aggregate the data. So this is widely referred to as the MOPE, or the modifiable aerial unit problem. Okay, so there's two different issues. One is the scale effects, so it's the level of aggregation, and then one is the zoning effect. It's like where you draw the boundaries. And I've just put a note here to basically say that the challenge occurs because during spatial analysis we aggregate data, and the results differ depending on the kind of level of analysis that we've applied to the same data. So you can have different aggregation schemes and it produces different results. So this is obviously concerning and something which you need to be aware of, because it means that there isn't one single precise, correct answer that can be generated. It changes depending on how you design the study. So every spatial process that you carry out, you need to be aware of the ramifications of the boundaries. So zoning's one issue, so that's where do you put the boundaries? And I've just provided you with an example of exactly what I mean here. So imagine these are the points that we want to sample. Let's just imagine that these are people standing in a line, just for the sake of something easy to understand. So they're not moving anywhere, it's just people standing in a line, and we just place one boundary set on top of them, okay? So in the top left-hand corner here, we basically have 6 points, 6 people. Within that box, we then have 2 people within the top right-hand box. The bottom right-hand box has 11 people, and the bottom left-hand box has 0 people, okay? So then if we take the mean number of people per box that we've got, we basically sum all of those and we divide it by the number of boxes that we've got, so we end up with a mean of approximately 4.75. Okay, fine, great. But the issue occurs, therefore, if I just nudge the boundary over, I nudge the boundary just a really small bit. Let's just say that this is a fraction of a degree. Let's just say that this is, tens of meters. But the difference is that with boundary set 2, we then end up with 8 people in the top left-hand box, 0 people in the top right-hand box. In the bottom right-hand box, we've got 13 people, because we also included that we now have the 2 additional people that were outside of the box before. And again, in the bottom left-hand box, we have 0. Okay, so basically if we take the summation of all of those people in the boxes and we divide it by the number of boxes that we've now got a mean of 5.25, okay? So you can see even just small changes in the boundary ends up producing different results, okay? So this is just a pattern that you need to be aware of. And one kind of serious outcome of this kind of boundary manipulation is actually with gerrymandering. So I don't know if you know what gerrymandering is, but essentially that's where the electoral boundaries are changed for electoral districts in order to give usually a preferred outcome for the incumbent party that's in power. So when a party takes power, what they might do is they say, we're going to review all of the political boundaries, and then essentially they change them all in their favour so that they're more likely to either stay in power or be re-elected in the future. And this just gives you an example here. So imagine we've got 50 precincts, and if you look at let's just say this is 10 by 10 square kilometers, and then basically 60 would vote yellow and 40% would vote green. Okay, if you look at the top part here, the center part where we look at the disproportionate outcomes from gerrymandering, on the left-hand side you would have 5 districts basically voting yellow if you had the horizontal boundaries. So yellow wins all these districts. But then the right-hand side here, if you change the boundaries in this kind of very specific way, then basically green wins the overall majority, because now what you have are 3 which vote green and only 2 which vote yellow. Okay, so this is just an example of how you can really change those zoning boundaries quite easily and actually sway the outcomes of elections, and this happens a lot. Far more than we would like. So there's some examples at the bottom here of how you would end up getting proportionate outcomes. So be careful of zoning reviews. Great, so that's kind of just some high-level examples of the different kind of theoretical aspects of the data that we need to be aware of when you're dealing with spatial data. Now what I've done is I've just placed that paper in which I mentioned previously in here for you to have a look at. So there's an archive link down here on the left hand side you can click on, and you can go there and look at the paper. But essentially it's the one that I mentioned where I was driving around passively sensing Wi-Fi access points. So we probably all have Wi-Fi access points in our house. So we have if you have a fixed broadband connection, then you'll have a Wi-Fi access point, and that's essentially what we then log on to in order to access our Wi-Fi at home. But because that's a bottom-up process, it emerges, we don't have a single overall understanding of how many Wi-Fi access points there are, and that matters because when you're engineering things like the design of them, or you're considering how to allocate the radio spectrum, so that's the invisible airwaves that we pass data over. So the FCC, for example, the Federal Communications Commission, has to make a decision over how it assigns the radio spectrum. And one consideration there is whether it should assign it to Wi-Fi uses like we have at home, or whether it should go to 4G or 5G, so to the big cellular providers, the AT&Ts of the world, the Verizons of the world, for example. So this study was really to go out and collect some data to understand the density of those Wi-Fi access points, and it just gives you a little bit of a flavour here. The map on the left-hand side gives you a flavour of where I was collecting them last summer in the United Kingdom. So there's a big patch around where I live in Cambridge, but also I collected data in London, all the way out west to Bristol and Bath, all the way up north to Leeds and Manchester. So I was just collecting it on my phone when I was driving around, and then basically using that data to understand how densely packed the Wi-Fi access points were. And because it's a density, it means that we need to unfortunately place a boundary on it, which is why we have the relevance of this paper for this particular point that I'm raising here in class today. So if you look at the panel of data that we have in the middle here, we have a range of different estimates for the number of APs that we've got, so the Wi-Fi access points mapped against the premises density by decile. So this is 10 being the most dense areas and 1 being the least dense, so that's from urban to rural areas basically. And then what I've done is I've broken down the data so that we have urban, suburban, and rural, and then we've got a different buffer size. Okay, so the key point here is thinking of the buffer size, because that's the boundary which we artificially place around those Wi-Fi access points that then we want to count. We want to count within each buffer that we place how many Wi-Fi APs are there and how many premises are there. Okay. And what's nice about this approach is that then if we look at the buffer size, so let's go to the very top of the slide here, so just to the top of this graph, so it's these 3 here. I've actually used a predictive model that I've developed in red. So this is how many Wi-Fi access points we think there are, and that should be relatively static across those 3 different buffer sizes. And then what we've got in the black is basically all of those hundreds of thousands of Wi-Fi access points that I detected through an app on my own phone so that I could passively sense where these assets were. And what's nice about this is that we really show, in effect, what's happening with the modifiable aerial unit problem, because we have higher densities down here where we've basically drawn a smaller boundary around those data points, so 100 meters. And then basically as we increase the boundary size, what we get is that the density actually decreases, and this is because we're getting differences in scale. So the reason why I broke these results down like this was that I wanted to be able to understand how changing the boundary was going to affect my results, okay? So that's basically saying we're not going to get a single answer. That's just not possible here. So I need to basically make a judgment call about what the right boundary is. I don't know what that is, so let's just show all of the results across those different boundary sizes. And that's how I ended up with these particular results. Okay, so that's just a flavor of what I was doing in relation to the modifiable aerial unit problem in this particular assessment. Don't worry about the prediction, the evaluation of the predicted model on the left-hand side. We're going to return to that later in the class, but if you want to look at the original paper, you can look at the archive link just here. Okay, fantastic. So let's think now about scale and aggregation. So it's, again, very similar. It changes your descriptive statistics. The variation may be systematic, predictable, or uncertain. So yeah, this is basically just re-emphasizing the point that I made in the previous slide. So if I asked you to go out and I said, please, can you take the average population for 50 states, or 3,144 counties, or 73,057 census tracts, or 217,740 blocks, you would basically end up with very different average populations for those different spatial units. But they're all measuring and counting the same individuals, okay? Right, you get that? But because of the aggregation level, we're ending up with different results. So we need to be aware of this particular issue. So I'm not going to spend much more time on this, just to raise again that there are these two different issues that we need to be aware of. Okay, let's move on now. So what is a fallacy? Well, a fallacy, according to the Oxford English Dictionary definition, is a mistaken belief or a mistake in reasoning that makes an argument invalid. And this is obviously important because, you know, we are scientifically minded. We want to make sure that we draw appropriate conclusions from the work that we're doing, that we build models appropriately, that we draw the correct inferences from those models, and therefore we don't want to make a logical mistake in our reasoning. Okay. That would be embarrassing. So a logical fallacy is where inferences on attributes or individuals come from group inferences. Okay, so that's a complicated way of kind of saying that you might make generalizations from a group to an individual which could be incorrect. Okay, so let me give you an example of that. New York State has a very high population density. Okay, you know, a lot of that is being driven by the fact that New York City is obviously so large. So depending on where you draw the boundary between, you know, 8 to 12 million people, so very large. So therefore, if I made the assumption that I made the assertion that an individual from New York City is from a dense city, that would be incorrect, right? Because that's not true. Everybody from New York State is not from a dense city. The reality is that if you're going to make this sort of assertion, you need to use a probabilistic-based approach. So you need to make a probability estimate that somebody is from a dense city. So first of all, don't make this type of assertion because it's incorrect. The correct way to do it, secondly, is to provide a probability for the likelihood that somebody is from a dense city if they're from New York State. And the way that you would do that is you would look at the locations of those people who lived across the state based on urban, suburban, and rural locations, and then you could make a probabilistic estimate just based on the share of the number of people that lived in a dense city. Okay, so if it was 30% of people in New York State who lived in a dense city, then you would have a 30% chance at drawing any one individual from New York State and that person actually being within a dense city. Okay, I hope that that's somewhat clear. We just need to be aware of making errors in the way that we reason. Okay. Okay, so moving on now onto the types of data. We've already spoken a little bit about this in general, so these are the fact that we have a variety of different quantitative and qualitative aspects of data. So we've worked a lot so far with quantitative in the lab work that we've done, for example, and obviously that's any data that can be expressed numerically. So it could be temperature in degrees Fahrenheit or Celsius, it could be rainfall in inches or millimeters, whether you preference imperial or metric units. But then equally, we could have qualitative data, okay? So we could have non-numeric data, and that's land use types. That could be levels of satisfaction. I think a good example within our area here is actually the Landsat data, and I think I come back to this later. So the Landsat data is basically it's a data set that's been gathered by launching satellites, and those satellites that are in orbit are able to look at the different, they're able to collect images of Earth, and then we're able to actually classify those land uses within the images based on information that we can gather from them. So it could be forest, it could be lake, it could be a settlement, like an urban settlement, and then we're basically able to put those into different categories, and that would be a good example of qualitative information in this regard. And data could be either spatial or non-spatial. Okay, so absolute spatial data is any data that has an explicit set of coordinates, for example. So if you think that we're all carrying around cell phones in our pockets, just think that pretty much anything that we do on a cell phone could have a set of lat-long coordinates associated with it. So it's like user X and user Y did these activities in this specific place because we've got lat-long coordinates that can basically just be pulled off the operating system. Particularly if you're using Android, then a lot of the apps that you're going to be using on your phone will be fully tracking what you're doing, where you're doing it, and basically taking all of that data, and then it actually uses that data as part of its business model for many of the main apps in order to make money. Okay, so remember, if it's a free app, then you basically are the product, okay? And you will get advertisements sold back to you, and the way that they do that is by collecting this data, and then the advertiser says that I want to specifically target my ads at people who do this thing or go to this place, okay? So just be aware that's the type of thing that's happening behind the scenes in your smartphone, and how we then kind of link together data in this way. So it's kind of it might be qualitative or quantitative, but it all has a spatial dimension. Okay, so we could have a variety of different types of spatial data as well. We could have implicit spatial data. So maybe this isn't something that has an explicit XY coordinate. Maybe that's data is not from a smartphone, so you don't have the privilege of having an XY coordinate, which is obviously a preference. But you do have data qualitatively which describes where it is. So that could be a street address. That could be information that it's carried out in a city or whatever, and then you're able to get some sort of spatial understanding from it. And then on the flip side, you've got non-spatial data. So this is just data that has absolutely no information about where it took place, and maybe it's got no temporal data as well. Maybe it's got no indication of where it took place in time. So this is kind of a difference between these two different types. Obviously, the latter part is not that useful for spatial scientists, but then again, I do use non-spatial data quite often to inform how I develop spatial models. So one good example is data released nationally. So imagine the Census Bureau isn't able to release some data because it's too sensitive at a spatial level, so it releases it for the whole of the states, or it releases it for the whole of the UK, or for the whole of Germany. In essence, you can still use that information in your spatial model, because what you may be able to do is somehow use the composition of that data to inform and the probability that a particular person in a particular time and space may meet a specific characteristic that you're interested in. Okay, so temporal versus atemporal data. So obviously temporal data, as we've already covered on, is anything that's pertaining to time, so anything that has a particular time aspect. So think back to the Fitbit data that I had, which had a time aspect. The market data had a very strict time aspect. Even the census data obviously has generally a year where that data is kind of relevant for. So this temporal data, the temporal aspect can change. It might be per second, per minute, per year. Obviously, there's large differences within that. But usually you kind of pick the right temporal scale that best suits your data, okay? Atemporal data, so that's basically data that's not associated with any time. So let's just say that that's the average speed of a species that you're tracking, or of, let's just say it's the average speed also of vehicles that you might be tracking. You might not have any specific temporal data. And then there's also this aspect of, well, is it spatially aggregated data, or is it data that's at the level of the individual? Okay, so you'll remember from the work that we did in R last week on data structures, and we had within our tidy data format, we had individuals as the rows across in a data frame, and that's, say that's a person level, so maybe you have specific characteristics for an individual, like I have blue eyes, I have brown hair, I'm about 6 feet tall. So essentially we can have that information at the level of a person, which is kind of as granular as you can get, and generally that's preferred, but it does introduce a lot of privacy aspects that we as researchers need to be aware of. So people don't often like having personal identifiable information out in the public domain, and therefore often a lot of the data that you might get from a data provider might be aggregated. If it's not anonymized, it might be aggregated to a level where it says that people who live in Fairfax City have these characteristics. Okay, so we don't have an understanding of who lives there. We don't have an understanding of the individual level data, but maybe it just says that 30% of the people who live there have blue eyes, 30% of the people who live there have brown eyes, etc., etc. Okay, so we might just get a composition for the data that represent a specific area. Okay, so I think that that's fairly clear for you now, so let's just move on. And then I think that this sounds like it's something that we haven't really engaged with before. What does discrete mean? Well, what we mean there is it's finite. I think that it's I think the description for what discrete is somewhat harder. So maybe let's just start with a continuous variable, because I think that this is easier for you to grasp. So a continuous variable is a variable that has an infinite number of possible values, and let's just think of it as something that can have an infinite number of decimals. Okay, so if I say to you, this is the amount of rain that we collected in 3 weeks, then that could actually be continuous in the sense that the amount of rain that we measured could go to as many decimal points as we really wanted, okay, depending on the level of precision that we wanted. So we could really drill down to a very a precise level of insight for that variable. Okay, and then that kind of contrasts with discrete, where imagine that we have some restrictions on the values. So imagine that we don't allow there to be decimal places. Okay, so you just have to work with whole numbers. So maybe then you're basically dealing with 87 millimeters versus 86 millimeters, and these would be an example of discrete variables. It has to fall into one of those integers. Okay. So maybe also it could be the number of people in a city or the houses on a block. And I think a good way to think about those numbers is that you can't have a decimal for a person, or you can't have a decimal for a block, okay? So you can't have 5.5 people, you can only have 5 people or 6 people, so you have to push it into an integer value. You can only have wholes, okay? So they're discrete. It's a discrete variable with a finite number of options for you to fill. Okay, so make sure you learn those definitions, that they are important. Types of data. Okay, so there's different levels of measurement that we might be interested in. So these are nominal, so that's basically categorical data. Ordinal data, so that's basically categories which have some sort of order within them. Interval data, so that's where we have continuous quantitative data, but maybe it's set around some sort of arbitrary point. And then we have ratio, which is your kind of classic interval, your classic quantitative data that you might get for area or distance. Okay. So for the nominal data here, as I mentioned before, that's kind of qualitative, descriptive, categorical types of data. The data are named generally as mutually exclusive categories. So I used before the example of Landsat. So if it's an area of forest, it can't also at the same time be an area of lake. Okay, so I presume that you kind of get that, and that's why we call them mutually exclusive categories. The data are collectively exhaustive. So every data value can be assigned to a category. It can't not exist in any category if it's in the data set. And it's only a comparison, okay? So that kind of gives you an understanding of what nominal data is. So you could think of that as the land use coding system or the names of countries. So whereas nominal data is just general categorical, ordinal data is similar in that it's categories, but actually it also has a specific type of rank order within it, okay? Which means that you're allowed to kind of understand that this one might be more or less than the one you're comparing against. So you could have strongly ordered ordinal data, so that's each value is given a rank order in a sequence. So imagine it's college rankings, or imagine that we're racing in a marathon and then we all ended up with a specific place within the finishes. So that would be strongly ordered, and you'd have a very clear indication of where they actually were within the overall distribution. Or you could have weakly ordered ordinal data. So essentially that's where you get a rating. Maybe you're trawling Google and you're looking for somewhere to stay and you get a hotel ranking. And whether you can trust it or not is a different kettle of fish, but that provides you with a kind of weak understanding of where it sits. It doesn't really say whether it's above or below potential other candidates. It just says it's kind of in this ballpark. All right. Interval data, so this is data in which you have a magnitude of difference that can be determined. So you can add it, you can subtract it, but the 0 point is arbitrarily assigned. So imagine that this is temperature data, so this is a good one. So if it's Fahrenheit, then the 0 point is essentially the lowest temperature obtained where you actually have a mixture of ice, water, and common salt. If it's Celsius, then your 0 point is basically the point at which ice freezes. Okay, so you can see what I mean when I say that these are arbitrary points, but then once you're on that scale, you're then able to make a decision about how one point can be different in magnitude to another one. Another one is dates, some more arbitrary. I mean, it's definitely, if you think of the calendar that we have, so the year is 2021, but that is almost certainly an arbitrary date that's been defined. If you look at the age of the Earth, for example, going back many millions of years, then actually the date that we use on a common basis is relatively arbitrary. Shoe sizes, these are another example of how these kind of sizes are relatively arbitrary. So if you look, if you're a US 11 or 12 shoe size, that's kind of, you don't really know what the 0 point is for that, okay? But it provides you some understanding that, if an 11 is too small for you, you might need a 12. And then finally, just to close with ratio data, this is data in which you have a ratio magnitude that can be easily determined. So you have a natural or a non-arbitrary 0 point. So for example, think of this in terms of distance or area. So if the distance is 0 kilometers, then you have a very clear 0 point, okay? But then if you have a distance of 1 kilometer or 10 kilometers, then you have a very good understanding of what the ratio is between those two different units, okay? That could be not just distance, that could be the precipitation amount that you get in millimeters, or it could be an area for a particular plot of land and you want to compare the two. So you have a much more straightforward way for you to kind of draw conclusions between these two different measurements. Okay. So let's just think about this in terms of a general data set. So for example, here, this is just a data set which provides the best college rankings for Michigan. And there's a national ranking for each of the schools here. So on each row, we have an entity, which is a university, in this case, a college. And then we have a national ranking, so that's where it sits nationally, for example, in the US. We then have, so the national ranking obviously is a strongly ordered ordinal type of data. And then moving on, we have the state tuition in dollars, the out-of-state tuition in dollars. These are all very ratio-driven data types. Okay, so very continuous, and they have a 0 point. And that's the same for undergraduate enrollment. But then for the year founded, then that basically is that's an arbitrary point. So in many ways, that's a type of interval data. Okay. So let's think about measurement concepts within data, and I just need to think of this, and just need to go over this with you very quickly before we finish. The way that this is kind of taught in the book and also in most of the courses is that people think about the way that you might throw darts at a board. That's fine. I mean, you can think of it that way, whether the thrower of the darts or whether you're shooting a target is precise or accurate. But I think we are in a spatial class here. So, I mean, I kind of would prefer if you would think of this as accuracy of GPS traces. Okay, so rather than thinking of this as a target, it would actually be, I think, easier for us in spatial terms if you think about, okay, I have a GPS satellite above my head, there's some trees in the way, it's going to make an estimate of my location on Earth, and there's an error, a margin of error within that. So let's think about that. It's trying to make an estimate of your location. And this matters because we want to use spatial data and we want to draw boundaries around maybe the number of people in a particular place. And if you're drawing boundaries and you've got error in the actual precision of those GPS traces, then you're going to have some people being allocated into the actual wrong spatial units for where they were located. Okay, so let's think of it in that way. So precision, so essentially the level of exactness associated with a measurement. So think of this in terms of maybe the number of significant figures, the number of decimal places that you might have in order to be precise about a specific measurement. So this is definitely affected by the quality of your instrument, okay? So you can see down here that we're not actually, so imagine the true location is the center of the circle. We're not actually accurate in terms of picking up the true location, but all of the estimates that we have for the location are actually all nicely clustered in the same place. So actually this isn't accurate, like we're not in the location that we should be, but we know that the estimate is precise because all of those estimates for our location are broadly within the same area, okay? And this kind of differs from something that might be accurate but not precise. Okay, so accuracy corresponds to essentially a value obtained from an instrument, and the difference between that and the true value. Okay, so let's say that our location is the very middle of this circle, and our GPS traces are broadly in the right area, so it's reasonably accurate, it's got us in the right place, but it's not very precise because actually each time it tries to make a measurement, it tries to estimate where we are in meters, there's quite a significant amount of uncertainty each time between the true value and the measurement that we're getting. Okay, so this is accurate but not actually precise. So you can think of this in 4 different ways. You can have something that's not accurate and not precise, so it's nowhere near the location that we need to be. And you could have something that's accurate but not precise, so it's broadly in the right area. Maybe if you averaged across all of those locations, you might get something very close to where you actually are. You could have something that's not accurate but is precise, which is like the first case that we had. So it's not in the right location, but all of the points that we collect for that location are actually fairly close to the margin of error that we have between there and the actual truth value. And then where we really want to be, which is incredibly hard, and to a certain extent this is the holy grail, is actually getting something that's both accurate and precise. And actually in the modeling work that we do, the statistical work, especially with human behavior, there's just so much uncertainty in the models. It's really hard to get something that's accurate and precise. Okay. So we can think about this in terms of actual numbers. So if we just think about these true distances here, let's say that we have a single true distance and that's 41.71 inches. Then if we have a range of other numbers in the first case, for example, they're all actually pretty close together, but they are quite a substantial amount of distance away from the actual true value. So this is very high precision. There's a lot of it's quite close together, and there's very little movement between each one of the points that we've got, but then it's not very accurate. It's not near our true distance. On the second part here, we have both high precision and high accuracy. All of the points are basically pretty close to the true value, and there's very little movement each time that we take a measurement. So it's quite precise. And then finally here, what we have is reasonable, quite good accuracy. It's generally moving around the truth value in a fairly reasonable way. I bet if you average it out, you probably get quite close to 41.71, but it's not very precise. So we have quite a large amount of movement around that truth value. So this is an example of work that I've been doing over the past year, which is assessing 5G rollouts in low and middle income countries. And it was actually a global assessment for every country, but it's quite hard to model every country. So what I've been doing is I actually modeled 8 individual countries, and then I use those results to inform the global analysis. I'll actually place the paper link in here for you to go and have a look at. But essentially, I was modeling a 5G rollout for Malawi, Senegal, Uganda, Kenya, Pakistan, Peru, Albania, and Mexico. Okay? And why I'm kind of bringing this up is that I was actually then estimating, well, okay, so most of these countries have some amount of 4G access, right? So the data services that we use on here, generally we're connecting where possible to a 4G service. It's quite fast broadband, but with 5G obviously it's going to be faster still, and we'd like to know how much we can viably deliver based on the level of revenue that's in the system and how much the infrastructure actually costs. So what I wanted to do was actually provide an indication of the percentage coverage that we could viably roll out 5G to, okay, by population decile. So just imagine we break all of the areas up in a country into the most dense, which is in the first decile, and then the last dense, which is the least dense decile. Okay, so we go from urban areas to rural areas. And essentially what I was trying to do was to actually make an estimate as to that commercial viability, but I had to make a call around the accuracy and precision, okay? So I know that there's a lot of uncertainty in the modeling that I'm doing, but therefore I actually opted to report my results at the decile level rather than trying to estimate at a more granular level. You know, I don't think that I can accurately, I don't think I can be as precise as me saying that the viability is 95.678% of the population that can be covered. So I needed to make a judgment call that I wasn't going to get into that level of detail, and I think that that's hard to do, to know what level of detail you should you should take. I think as a PhD student, you always think that, oh great, my model's really precise. But the reality is that you probably don't have the accuracy to be really precise, so you just need to provide general oversight and numbers, and that's exactly what I've done here as an example for Peru, for different levels of broadband capacity using different technologies, whether it's 4G or 5G. I'm able to kind of take a baseline case for how we think commercial rollout will take place, up to maybe 70% of the population or 50% of the population. And then we're able to implement all of these other strategies which test how maybe the viability is improved, maybe via sharing infrastructure and reducing cost, or reducing the cost of buying the spectrum licenses so that they can sell the services, or reducing the corporation tax rate, okay? So this is just a general overview of the types of decisions that I've had to make in my own work. And actually, I just took an example from LinkedIn about why you need to be sensible about precision. Okay, so this is a new report that came out, which was focusing on large enterprises building their own dedicated 5G private network without a classic mobile operator such as Verizon or AT&T. So imagine they just do it themselves. And actually someone who I've been publishing with recently made this very good comment, which is that they'd estimated that by 2027, which is obviously a very long time away, 6 years off, that it could be 7 billion. So $7,082.1 million by 2027. So there's no way that you can be this accurate. No way you can be that precise when you're dealing with A, forecasting that far out, and B, the types of models that we're using. And actually, my friend said anyone trying to do forecasts with 5-digit accuracy on a 7-year horizon is mathematically clueless. That really doesn't inspire confidence. So you really have to make a good judgment call here. It's not a bad thing to reduce the precision of your estimates. In fact, I think it's wise. You don't want to be trying to be really precise when your model is not very accurate. Okay. Great. So just to close off now, validity. So when we kind of say we're going to measure a process or something with a particular data variable, we need to make sure that that variable actually measures what we want it to do, okay? So imagine we were interested in studying the quality of life in a city. We need to think about, well, how is quality of life defined, and then what's the proxy that we have for quality of life? And this can be really hard, and validation as a consequence is a long, drawn-out process, and it's what keeps modelers up at night, because if you've drawn conclusions from a model and you've not validated it correctly, then basically you're not measuring what you think you're measuring. Okay. I've just returned, as I said I would do, back to the Wi-Fi war driving paper, and that's because what I do in this bottom left-hand side here is I actually take the predictive model that I've built for the number of Wi-Fi access points, and I compare it to actual Wi-Fi data that I get. So for buildings at the University of Cambridge, which is where I got the data from, then essentially they gave me information which is the number of Wi-Fi access points per building, and I was able to compare it with the model that I'd built to look at the general trend. And I argue that generally the general trend is quite similar. There's obviously some uncertainty in the predictive model, but generally this shows that as you essentially increase the size of the building, my predictive model would estimate that there's more Wi-Fi APs, and that actually matches quite well the actual data that we have taking place. Okay, and actually I didn't discuss before, but if you were interested in wondering what war driving is, then you can take a look at the paper where I provide a description of that. So essentially there's a film in the 80s where a person dials all of these telephone numbers to work out how many internet modems there are when there really weren't very many, and that's how it ended up with this name. But essentially in computer science, this is a very common way to go out and collect data on wireless access points. So you're driving around collecting data passively, okay. And then finally, just to finish, reliability, well, that's how consistent and stable your data measurements are, okay. So you need to be able to check this, and it's really important because if you don't have decent reliability, then there's going to be a lot of error in your estimates, and that may lead to you making the wrong decision, okay? So that's about it from me. Thank you very much for tuning in today. This has been the second lecture where we basically discuss different aspects of spatial data. In the following lab now, I'm going to move on to descriptive statistics, and that's going to kind of set the landscape for the next piece of work that you have due after this week's assignment. So the following one will be on descriptive statistics, but it will pick up a lot of those aspects that we've picked up over the past hour or so, and hopefully put you in a really solid position in order to kind of get an understanding for those quantitative metrics that we're interested in when we're undertaking descriptive statistic analysis. Okay, so thanks for tuning in. It's been great to see you, and I'll see you all soon. Goodbye.